I bet you didn't know that we would be talking about something called H3O. Yes, that is H3O, not H2O, but H3O. And believe it or not, whenever you're testing for acids or bases, if it comes up acid, it has produced H3O, and that should have a little positive sign here. It is an ion. An acid, by definition, is a substance that donates helium, or not helium, but hydrogen ions to transform H3O whenever it's mixed with water. So add this to water and it becomes H3O positive. That's what an acid is by definition. Now, most acids in foods are very dilute, which means they don't have a whole lot of concentration, and they're not terribly harmful. In fact, most of them would only burn your eyes, like lemon juice would burn your eyes if it got into it, but it's not really that harmful. But even those acids can burn sensitive areas like eyes. But if you really get a highly concentrated acid, it could even burn the skin. And because we have these charges, acids conduct electricity when it's dissolved in water. The stronger the acid, the more electricity it conducts because you have more H3O ions. The weaker the acid, well, it doesn't conduct electricity quite as much. But let's take this formula down here. We have HNO3 plus water turns into H3O. See, it donates a hydrogen, and you're left with plus NO3, which now is an ion. So what these acids do, these acids donate a hydrogen. So every acid is going to have a hydrogen in it. That's one way you can identify acids. It's going to have a hydrogen in it. So it can donate that hydrogen and make H3O. Now, not all react. Oh, I'm getting ahead of myself. Car batteries are a little bit like this. Electricity is conducted through car batteries. And you notice you have water in car batteries. I don't know if you're very familiar with it, but if the battery gets a little weak, you actually pour water into these top parts here. So what happens is it has this acid in it, not this particular acid, but it has an acid in it, and you pour water in it, and the more water you pour, the more opportunities to make H3O that you actually have. So you just pour water in and it adds more kick to it, I guess you might say. Now you have weak acids like this. And the weak acid, well, this is actually acid here. This is a strong acid. This is a weak acid. You can tell in the formula it's a weak acid because you have these reversible arrows. You may remember when we talked about these reversible arrows before, it means you kind of have a state of equilibrium. You have some of these which go to this side, some of the H's which are going to go to form H3O, but it's not going to be all of them. Kind of forms a state of equilibrium. This is going to be a weak acid. And this one's going to be a strong acid because it has just the one arrow there. Oh, what did I do? Well, anyway, well, that looks weird. I'll just move this around. Because of this, it's going to be a strong acid. And I will write strong up here because of that arrow. That arrow means that it fully, all of this HNO3, all of the H's are pretty much going into making H3O. So there's not really much equilibrium here. Acids taste sour, like lemons and pickles. Pickles are not acidic, but they are soaked in vinegar. And the indicator actually tests for H3O. So when you have things like litmus paper, which is going to test the acidity of something, it's testing how much H3O is there. Now let's talk about a base. Base, as you know, is opposite of acid, but they're both dangerous. So don't assume you can like drink bases as frequently as you could, infrequently as you could drink acids and stuff like that. And both of them make ions. Now bases, often you will have an ion that looks like this. They don't form these though. They don't form the H3Os. Many bases either contain or make hydroxide ions, which is OH. So a characteristic of an acid is that it has H's to give, and characteristics of bases are that they have OH's to give. So sometimes you can just look at the formula and see whether it's more acid or whether it's more base. Since you have this electrical charge, yes, they also conduct electricity. Acids conduct electricity and bases conduct electricity. Strong bases, just like acids, strong bases will conduct more electricity than weak ones. And you can probably imagine that this one right here is a strong base. It lets go of this potassium, so it ends up with this OH, this hydroxide ion. And you can probably guess, because of the reversible arrows, this is a weaker base. This is actually ammonium here. Ammonium with the water is going to add another, take a hydrogen away from water, and it's going to leave the hydroxide ion. They taste bitter, bases do. You have this strong one right up here, and you have this weak one right up here. I'm checking my notes to see that I have it all in here. Okay, now we're going to go to a different slide. This one talks about pH. pH happens to be up here, and you may know that the test for acids and bases reveal something in a term called pH. pH indicates the concentration of H3O ions. Remember, if it has H3O ions, it's going to be acids, and OH ions. Remember, if it's OH, it's going to be bases. So any pH indicator is going to identify whether it has a lot of H3O, hydronium, or whether it has a lot of OH, which is hydroxide. So that's what a pH measurement is. If you are a neutral solution, like water, your pH is 7. But if it is less than 7, it's going to be an acid. If it is greater than 7, it's going to be a base. Now it only goes up to 14, so you can anywhere 7 through 14 would be more on the basic side. Now you have litmus paper here. Litmus paper, if I'm thinking correctly, if it is blue, it is more basic, and if it is red or pink, it is more acidic. Here's what litmus paper looks like. Checking my notes to see if I'm forgetting anything. Apple juice, for example, has an acidity of 3, or a pH of 3. We have coffee here, which has a pH of 5. And we have these Tums or Rolaids or whatever the antacid is, which has a pH of 8. So the apple juice and the coffee would be more acidic, and the Rolaids would be more basic. But even though it looks like these numbers are close, they aren't really that close. Apple juice has not only well, it's kind of like the Richter scale with an earthquake. Apple juice is 10 to the second power more acidic than coffee is. 10 to the second power is 10 times 10, so that would be 100 more times acidic than coffee is. If it were, like for an example, this case, coffee being 3 digits down would be 10 to the third times more acidic than these antacid tablets, which is 10 times 10 times 10, which if you just add the zeros correctly, I believe that would be 1,000 times more acidic than these antacid tablets would be. So that's how it works right there. It's really quite a bit of a jump there. Let's talk a little bit about neutralization reactions. Neutralization reactions are reactions between H3O and OH. And you can imagine what happens when you have H3O and you put OH with it. It's going to form water. So it basically takes something that is an acid and takes something that is a base and puts it together and makes something that is neutral, which would have a pH of 7. Now, you're not just going to find these floating around very often and put them together. They're going to be in formulas like this, where you actually have other substances that go with it. And when you have a neutralization reaction, it always forms a salt and water. So it's usually not going to be like this one. This top one is going to be like this one. Here you have the sodium and the chlorine, which are going to end up being put together, and you'll have these, which are making the water. So a neutralization reaction would be acid plus base yields a salt plus water. That's exactly what it's going to end up being. Let's go to another slide. Okay, let's see what of these are acids and what of these are bases. Shampoo, that's a base. Vitamin C, that's an acid. This is ammonium, a house cleaner. That's a base. Soap, that's a base. Dye in your clothes, that's an acid. Baking soda, base. Aspirin, acid. Baking powder, base. Meat tenderizer, acid. Clorox, bleach, that's a base. Detergent, that's a base. Fruit juices and fruit, that's an acid. Hey, notice what you have here. You have a lot of these bases, which are cleaning supplies. So the soap is an emulsifier. Hey, you remember emulsifiers. Emulsifiers take two things which don't really go together and help put them together. And what they help put together is water and oil. We naturally get oil exuding from our skin, and water doesn't seem to wash it off very well. So that's why you would need soap. It's an emulsifier that gets the oil off of our face and off of our body into the soapy water, and it then washes away. Detergent kind of does the same thing, except it works better in hard water. We'll mention hard water later on. It has some stuff in the book about hard water, but it kind of does the same thing as soap. It's an emulsifier. Ammonia does similar something. It is an emulsifier for greasy dirt. Baking soda and baking powder, well, they're also bases. Not going to talk much about them. Bleach and other disinfectants, they kill bacteria. Now, shampoo is often pH balanced. Now, sometimes you can have a shampoo that is as high as 8, but when it comes to cleaning hair, people generally like their hair to be shiny. So the lower the pH, like down in 5 and 4 area, it's not going to leave much shine. So they usually have the pH a little bit closer to 7 for shampoo, just so it can leave hair shiny. Too much base will take away the oil. Acids, vitamin C and aspirin happen to be acidic. Clothes often get their color from an acid, and sure enough, acid tenderizes meats. And something I forgot to put on here, it helps make yogurt. Hey, I hope you've learned a little bit about acids and bases.